Hi, my name is Daniel Fontaine, and this is my midterm for 2160 Embedded Design project video. Okay, for this project, we were required to take this 4x4 keypad and using Cordis, design hardware so that the inputs of the keypad would appear on the hexadecimal display as so. So as you can see, for my hardware design, I have 4 inputs and I have these 4 outputs right next to them. Now these correspond to the 8 leads right here coming from the actual keypad. The 4 inputs are the 4 rows of the keypads, while the 4 columns are the 4 outputs of the keypads. The inputs of the keypad are intrinsically high, which is why each of them require a NOT gate to make them low. And when the button is pressed, they become low, whereas a NOT gate then turns into high. Now all of these inputs come into a 4-bit decoder, which you can see right here, as the inputs are always 1000 or 0100 or any variation of that. Either way, only one of the inputs is high. So this decoder, using 2 OR gates, 1 AND gate, and 1 NOT gate, can transform all of those inputs into a 2-bit representation of either 00, 10, 01, or 11. Here are some examples of the decoder. So if this final input is 1, this one will come all the way here and all the others will be 0. And that would be a 1 here, a 1 here, meaning 1, 1. If this input is 1, we will get a 1 here, making this OR gate 1. We would get a 1 here, a 0 here, making this a 0, and a 0 here, making it 2 zeros, making this 0, 1. As you can see, all the variations will go through, and each of them will create one of those unique 2-bit outputs. Now, this is not the only use for the inputs. As you can see here, when we scroll up, all the inputs are named after their specific NOT gate, and those inputs come down here into a 4-bit OR gate, which the output is named press. Now press is used to stop the scan of the column mux and to enable the display. Now scrolling back up to the outputs, we have these 4 outputs. All these 4 outputs are connected to result, which comes down here and comes from this mux. Now this OR gate down here at the bottom left, as you can see, enters a NOT gate before entering scan. That means 000 becomes 0, becomes 1, enabling the scan, allowing the mux to scan through all of these different inputs, which represents one of the 4 columns. This is the first column, second column, third column, and fourth column. And as you can see, when no button is pressed, they are all scanning, meaning all the columns are all the columns over here are 0, and they all transform into 1s. And these 1s are outputted on these 4 LEDs for us to see right here. So I can see all 4 of them are 1s. Now, the way the keypad works, a single button press wouldn't be able to be recognized unless the keypad had a 0 state. And this mux scanning through currently creates that 0 state, so that button can be recognized. As you can see here, we have the 0 state, and then when a button is pressed, the column is recognized, a different column is pressed, different column is recognized, so on and so forth. Okay, returning back to press as seen here, when a button is pressed, either one of these will make this a 1, making it a 0. This stops the scan, which is scanning at the rate of the clock, going from 0 all the way up to 3, or 1 to 4, scanning through all 4 of these. This stops the scan at the correct one of these columns, which displays a 1. Alright, so then once again, these inputs are 7 in bit, 11 in bit, 13 in bit, and 14 in bit, which is 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, and 1, 1, 1, 0. Now, these inputs are then flipped, and as you can see, when they're flipped, they mirror the same inputs as our row inputs. So now that our column inputs mirror our row inputs, they can go through the exact same decoder right here that our row inputs went through. changing the columns to a 2-bit representation, just as we did with the rows. After both inputs are converted into 2-bit representations, as we can see here, the row inputs go to these bottom two, and then these top two from the columns go in here into a 4-input display. Now, if we go up here to select the display, what we see is the 4 inputs. And what we see is a total of 16 AND gates. Each one of these AND gates represents a button on the board. If we go to one of the buttons, let's see, if we go all the way up to 1, as you can see here, 1 is 0, 0, 0, and 0. That is because when we press the button 1, if we go back, 1 will be all the way over here. 1 will be equal to input 0, right? This is D0. Then we go back to our decoder, which would be D0. This would turn 1 into 0, which would be 0, 0, 0, 0. And down here, it would be that none of these would be selected, so this would be 0, 0. So the 4-bit representation would be 0, 0. Then we go back to the midterm, come over here, and we look at the mux. 1 is in the first column, right? So that means that column 1, or 0, 1, 1, 1, would come here and flip to once again be 1, 0, 0, 0, which again would be all zeros. So now this display, that's not what I meant to do, sorry. This display right here, this AND gate would be 1, and this one comes around here, and as you can see, it is connected in 2 places. Now, if we scroll all the way down, these OR gates down here represent the actual segments on the segment display. 1, as we look at on the board, is only 2. So up here, it's only connected to 2 segments, as only 2 segments need to be on. Okay, so that is how they're displayed. Now, going back outside, if we come here, you can see there are actually 5 inputs to display. There's this enable input, which is connected to press. As said earlier, when either button is pressed, this press will become 1, and this will enable the outputs. As you can see, when no buttons are pressed, even though the board is showing a high state of all the rows, there is no output because it's not enabled. So if we go back into this display, we can come all the way down, and we can see that there is an enable input which comes through this NOT gate and is connected to the output of all of these OR gates, representing each one of the segments. So this is how the enable works. And then we come here, we can see these 2 are the OR gate representations of A, these 2 are B, these are C. And then when we go look at here, the way the 7-segment displays is that the very top right here is A, then we go B, C, D, E, F, and then in the middle we have G. So those are the 2nd segments, and here are the 7 segments. Now the final thing that we need to talk about are the actual pins. And if we come here and we go to your pin planner, we can see all of the pins that each of ours are connected to. So now the outputs, we can also see them here. The outputs are connected to the 7 pins for the first hexadecimal display. We have 8 here, which are pins for, these 4 are for an LED to show when a button is pressed, and these 4 are an LED showing when a column is selected. These were bug decoding outputs and are not currently needed. These 4 outputs go to the row, and these 4 inputs go to the, these 4 outputs go to the columns, and these 4 inputs go to the rows. Now, when we come down here to the actual board, the board is placed on the GPIO extender, and this extender has a space in between a 5-volt and a 3-volt constants, which is perfectly spaced 8. and that is where our board is pressed. And if you want to know the actual representations of each, starting at 1 here, going from bottom up, the first 4 are the rows, and then the next 4 are the column inputs. All right, now is for the fun part, the moment we've all been waiting for, which is the actual demonstration. Now, I've been showing off 1 quite a lot, but I will just go through here. Here we have 1, then we come here to 2, press, hold, 2, 3, A, here's 4, 4, 5, 6, B, then we go up here, 7, sorry about that, 8, 9, C, then star here is actually E, 0, hashtag here is actually F, sorry, the button's a little stuck, and then down here we have D. So there is my board working. You can also do 2 buttons same time. So this one is going to save the first button's input, right? So if we press 1 and then you see me press 6, down here we will still see 1, then I let go of 1 and show 6. So 1, press down, still 1, let go, 6. Okay, we come over here, we do 0, and then we press C, let go, C. Okay, fun fact about this, I don't know if I talked about it in my display, but my display actually has inverters after each one, and when I just finished working on it, my display would actually show everything but the representation I wanted. So that was a pretty easy fix. But so yeah, so 1 would be literally everything but those 2. But yeah, as we can see here, oh, another thing we gotta do is we gotta try 2 columns. So 2 and then 5. As you can see, the 5 lights up, but 5 does not display. It stays as 2. One thing about the same column though is that if we go 2, then we go to 8. If we go, yeah, so if we go 2 and we go anything below the one right below it, it will display the second one. That is a bug I was unable to fix. And then finally here, another bug I was unable to fix is the same row, which will 2, and then if we press A, it will switch. So yeah, try to do 2 and A at the same time. Those will turn off, and that is due to the way the entire circuit is designed. This row will no longer become low as we needed at the beginning. This needs to become low to go. The row will no longer be low if 2 buttons are pressed in the same row. So it's impossible to try to display 2 buttons in the same row. However, 2 in different rows, different columns are easy. 2 on the same column, we get 2 rows apart, it gets a little bit more difficult. Anyway, I appreciate you taking the time to listen to me here. It was a fun semester. I don't think I'll be posting much anymore, but like and subscribe if you want to, below the video up. Thank you.